All right, on this video, I'm going to show you how to use your matrix from your Excel spreadsheet to calculate the chi-squared and then to draw a conclusion for your test. So I have copied my matrix over with the totals, and the first thing you need to do is create the same table but of expected values instead. So these values that we just wrote in our matrix are called the observed values because they are the values that you actually observe by researching your data. To create the expected frequency table, we have the same exact rows and columns, so you still want to have a low, medium, and high for your x variable, low, medium, and high for your y. And this table is going to show you what those values would be in each cell of the matrix if everything was evenly distributed according to probability rules and not according to actual, real life facts. So the way you want to do it is to take, for this cell of your table right here, you want to take the row total, which is 36, and multiply it by the column total, which is 38, and then divide that product by the total, which is 113. So it's going to be 36 times 38 divided by 113 for my data. For this cell, it'll be the same row, so 36 again, but now multiply it by the column total, which is 36. So 36 times 36 over 113. And then, of course, this final cell will be the 36 multiplied by the 39 divided by 113. I'll go back and actually calculate these after I fill in all of the work. And I do want to see this work for your project, so if you need to show it on a separate piece of paper and then scan it in, go ahead and do that. You can also find a way to type it in if you're comfortable doing that. The next row, the mediums, the total is 39, so it's going to be 39 multiplied by each of those columns. So 39 by 38, 39 by 36, and 39 by 39, all divided by 113. And then for the final row, the high GDP, that row total is 38. So it's going to be 38 multiplied by each of those column totals. So 38 by 38, 38 by 36, 38 by 39. And the reason these numbers are also similar is because when we did our matrix, we tried to divide our data pretty evenly into thirds. So your numbers are probably all around 33, 34, 32, in that region. Okay, then you want to take out a calculator and actually calculate the value of each of these fractions and give your answer as a decimal to 3 significant figures. I'm going to change to red so you can see what they come out to. This comes out to 12.1, 11.5, 12.4, 13.1, 12.4, 13.5, 12.8, 12.1, 13.1. And so you can see what the values would be if only probability determined internal death rate and GDP. So if you look at my data, it's fairly different, particularly in the low GDP and the high GDP category. My values came out to 1, 10, and 25 in the low GDP, when the probability would have predicted them to be 12, 11.5, and 12.4. So they're pretty different. Same with the high GDP. So these are the expected values versus the observed values. The reason we need to use both tables is because the formula for chi-squared, I need to write the formula here, is the sum of each observed value minus its corresponding expected value squared over the expected value for each cell of the matrix. So there's 9 of these calculations altogether, and then of course the giant sum of these, you're going to add your 9 fractions together after you generate them. So I'm going to fill in a few of those so you can see what the chi-squared calculation should look like. So chi-squared is going to equal, for my values, the first observed value, which is 1, minus the first expected value from the same cell, which is 12.1. Let's go down to the bottom here. 1 minus 12.1 to the second power over 12.1. Notice I didn't put the sum in front because now I'm actually going to change it to a bunch of plus signs. Plus the next observed value from my actual table was 10. And the expected value that goes with that is 11.5. So we fill it in as 10 minus 11.5. Make sure you're putting that in parentheses when you square it. divided by the expected. The next one is going to be that 25 that we had here, as compared to 12.4. 25 and 12.4. Square that, so 12.4. And then you go down to the next row of your table and do that row as well. So it's 13 and 13.1. We put together. And I'm not going to go ahead and fill in all 9 of these. So that's what you would need to do. You need to fill in all 9 fractions for all 9 cells of your table with plus signs between them. Figure out what each fraction is. You can do them as decimals if you want. Add them all together and write your final chi-squared value, which is the sum of all those fractions, as a decimal to 3 significant figures. So when I finish my calculation, adding all those together, it comes up to 41.6. There's no units on this. It's a number that you're going to compare to the critical value for your study. Because I'm doing the 5% significance level and I have 4 degrees of freedom for my table, my critical value is 9.488. I got that from a statistical table that we went over in class. You can look up that statistical table on the internet. It's based on basically how many cells are in your matrix, and it's based on the significance level that you want to perform your test at. And we are asking you all to do the 5% significance level, and all of your tables have the same number of matrices, so we can all use the same critical value for our survey. So just the thing that I just wrote in red, that's the number that you want to use to compare your chi-squared value. So you want to take 41.6, which is my chi-squared value, and compare it to the critical value. By compare, I mean determine if it's greater than or less than. Depending on the comparison, you're either going to accept your null hypothesis, which says the 2 things are independent, or you're going to accept your alternative hypothesis, which says that the 2 things are dependent. And here, because it's greater than 9.488, I am going to accept the alternative hypothesis. This is the conclusion that I'm drawing to my study. Accept the alternative hypothesis. That maternal death rate is dependent on GDP. So your Y value is dependent on your X value. Or if your chi-squared value is less than that 9.488, you're going to accept the null hypothesis, which is that your Y is independent of your X. And then I want you to go ahead and explain in a nice thought-out paragraph why you think, given your data, you got the result that you got. And that would be the end of the project.